Hey everyone, welcome back to probability theory. This will be lecture 28 of the course. And in this section, we just want to take a minute to briefly introduce another probability distribution that is useful, and that is the beta probability distribution. So let's go ahead and jump into it. And we'll call this section 3.6, the beta probability distribution. So the beta distribution is kind of similar to the gamma distribution. So it's similar to the gamma alpha beta distribution. The difference here, really, the main difference, well, it's going to have a totally different PDF. I mean, it's defined differently, but functionally speaking, the big difference here is that it's going to be limited to the interval 0, 1. So, but is limited to the interval 0, 1, or open interval if you like, or closed interval can be done either way. And so the main use case here, well, one of the main use cases is in modeling proportions. So big use case is modeling proportions. So things like the proportion of a chemical that does and does not have impurities would be an example. So e.g. things like modeling the proportion of a chemical that does and does not have impurities. Right? So this is an example. There's countless examples, of course. And so let's go ahead and define the gamma distribution. A random variable y has a beta distribution if and only if the density function is equal to y to the alpha minus 1 times 1 minus y to the beta minus 1 divided by beta function the beta function evaluated alpha beta. Okay, and that's going to be true for all y between 0 and 1, and the density is 0 otherwise. Okay, and so this is the PDF. Now here, just like the gamma function, we have this function within a function inside the beta function. So what is this thing? So beta alpha beta, or b alpha beta, however you want to denote it. This is another integral similar to what we saw with the gamma function. So in this case, it's equal to the interval from 0 to 1 of y to the alpha minus 1 power times 1 minus y to the beta minus 1 power. Okay, and it turns out that this is equal to the gamma function evaluated at alpha times the gamma function evaluated at beta divided by the gamma function evaluated at alpha plus beta. Now, you could go through the effort to see what that's about. I recommend looking into that. It is kind of fascinating. But just in the interest of time, and given this is something of a minor distribution in terms of our named continuous distributions, we're not going to jump into it. So this is the PDF, and within the PDF you have the beta function, which looks like this, which is a derivative of, well, not actually, but it's based on the gamma function. So it's a combination of the gamma functions from the previous lecture. Okay, and so then what about the mean and the variance here? Well, so let's let y be a beta a beta random variable with parameters alpha beta. Then the mean or the expected value of y, is equal to alpha over alpha plus beta. And the variance of y is equal to alpha beta divided by alpha plus beta squared, quantity squared, times alpha plus beta plus 1. Okay, so not as easy to remember as the gamma function, but that's all right. And so this is our beta random variable. The similarities to the gamma function are quite notable when you plot a few of these. And so let's see what this thing kind of looks like. We'll just plot a couple curves here, approximations to what the beta random variable looks like. So remember, it's defined on the interval 0 to 1. Right now, if I set alpha equal to 2 and beta equal to 5, then I get something that looks kind of like this. Okay, so it's got a little bit of that right skew, looks very gamma-like. Of course, it's censored on both sides, right? Obviously, it doesn't go below 0, similar to like the gamma distribution is censored on the left. But here we're also censored on the right side. We don't have any density above 1. Right? So that's an example of what the beta function looks like with these parameters. What happens when I change them? So let's adjust these up a bit. Let's adjust them down actually. Let's go with alpha equals 0.5 and beta equals 0.5. Now when you do that, you get something that looks like this. All right, so the density is all kind of located on the edges, right? So the probability density is close to 0 and close to 1, and it kind of dwindles in between. Okay, so it's a very different kind of shape, right? Another example would be, let's look at this one, right? So if I set my alpha equal to 2 and my beta equal to 2, then I get this like perfectly symmetrical dome like this. Right, so all my density is kind of like this dome shape. Okay, and so of course there's like countless variation here, but the key thing is that these parameters can be set to match the actual observations in the data, and you can establish which beta distribution best fits the sort of data that you're looking at, and obviously also it has characteristics of the gamma distribution for some settings, and for others it's quite different. Okay, let's do an example where the beta distribution is useful. And so let's take a look at this example. An exam for undergraduate math students has an average of 80%. So an exam for math students has an average of 80% and can be modeled using a beta distribution. So we'll say beta, and actually give the parameters here. Alpha equals 4 and beta equals 1. So the exam scores can be modeled using a beta, alpha 4, beta 1 distribution. Okay, so we've got this set up. Now what does this actually look like? So if you were to either figure out how to plot this yourself or use some kind of a tool, what you'd find is that the distribution looks a bit like this. Okay, so it's something like this. Right, so the average is up here by about 0.8 as it's given. 80% is the average, and so this kind of makes sense given that piece of information. right? And obviously, you can't do better than 100% on the exam, so you got this like hard cutoff at 100%. You can't do worse than 0%, so you've got obviously this cutoff below. And so this is the kind of a visualization of the distribution. Now, we can talk about the mean here. We know that it's 80%. So we know also that the mean of a beta distribution is equal to alpha over alpha plus beta, right? And so we can plug those values in. That'd be 4 over 4 plus 1. So it's 4/5. So that's 80%. Makes sense. Okay. So given that, right? Now, what's the question here? Well, let's find the probability. Let's find the probability that a random student scores less than 60%. Okay. Okay, so that's what we want. So we'll let y be the student score. It's a random variable. Okay. And we know that y is beta 4,1, right? That information is given. So what's the PDF look like here? So the PDF here is 1 over beta 4,1. Okay, the denominator, remember, has that down there. Times y to the 4 minus 1 power times 1 minus y to the 1 minus 1 power. Okay, and so this all kind of simplifies down into 1 over beta 4,1 times y cubed. So remember that beta 4,1, this is the beta function. Okay, so let's remember what that is. So alpha beta is equal to gamma of alpha times gamma of beta divided by gamma of the sum, alpha plus beta. Right, so in our case, that's going to be gamma of 4 times gamma of 1 over gamma of 4 plus 1, which is 5. Okay, now, if you remember from the previous lecture, we talked about how to quickly evaluate the gamma function. We know that it's a factorial. Right, so we know that this is 4 minus 1 factorial. This is 1 minus 1 factorial. And this is 5 minus 1 factorial. And so, of course, you got 3 factorial over 4 factorial, which is equal to 1/4. All right, so in this case, our beta 4,1, this guy here, is just 1/4. Okay, and so we can kind of take that and plug it in up here. So that means our density function for this beta 4,1 distribution is 1 over 1/4 times y cubed, otherwise known as 4y cubed. Okay, so then the probability is easy to find. We're interested in the probability that y is less than 0.6. Okay, that's just equal to the integral from 0 up to 0.6 of the PDF, which is 4y cubed. Okay, so that is 4 over 4 times y to the 4th from 0 up to 0.6. Okay, so we've got y to the 4th from 0 to 0.6. And so that is just equal to 0.6 to the 4th power minus 0 to the 4th power. And if you were to crunch those numbers, you would get 0.1296. Okay. So the probability that a randomly chosen student scored less than 0.6 is about 13%. Okay. Very good. What if I want to know instead the probability that y is greater than 0.9? Right? What's the probability that a randomly chosen student did better than 90%? Well, that's just the integral from 0.9 up to 1 of 4y cubed, right, which is y to the 4th power from 0.9 up to 1, which is 1 to the 4th minus 0.9 to the 4th. And so you get something like 0.34. Okay, so about 34% chance, right? It had a high average of 80%, so that makes sense. Now you can do things very specific, like maybe I want to know the probability that 0.8 is less than y, which is less than 0.82. Now, of course, when you get down into really tiny slivers of the distribution, of course, the probability is going to decrease, even if there's a lot of mass underneath the curve at that location, right? And so in this case, this is just another integral from 0.8 to 0.82, and again, it's 4y cubed dy. So that's y to the 4th power from 0.8 to 0.82. Okay, and so it'd be 0.82 to the 4th power minus 0.8 to the 4th power. And when you do that math, you'll see it's about 0.043. So it's about 4.3%. So about 4.3% of the students scored between an 80 and an 82%. Okay. So this is just an example of using the beta distribution. I think we'll end with this. Again, this is super useful, particularly if you are dealing with a distribution with some skew or some kind of weirdness, and also it is limited to a finite interval between, particularly between 0 and 1, but even if it's any finite interval, adjustments can be made to the distribution to make it fit. So we'll leave it there, and next time we'll get into some discussion of additional ideas regarding expected value. So take care until then.